Welcome to this second tutorial on circles. Now the first tutorial was focused on geometry and sort of looking at triangles inside circles. This tutorial is mainly going to be on thinking about pi and using pi to understand the circumference of a circle and the area of a circle, and then looking at parts of circles which are called sectors and being able to work out the what's called the arc of a sector and its area. We'll also touch on a related topic at the end. It's really sort of an add-on, to be honest, and that will be polygons. So let's start this tutorial as with the last one, which is to draw a circle. What better way to start any tutorial, you might ask, really, because the circle is the perfect geometrical figure, and there it is, and it's so easy to draw with a pair of compasses. Now, we talked in the last tutorial about the diameter, which is a chord that passes through the center of the circle. So let's label that D, the diameter. So this length here is D, and now I want to talk about the circumference of the circle. The circumference let me call it C, so namely the perimeter of the circle is equal to a number times the diameter, and that number we represent by a Greek letter pi, and that number pi is one of the best studied numbers in all of mathematics, and it has the value 3.14159 ... and it's an irrational number, and as you know from the tutorial on numbers, given it's irrational, these decimals these digits don't repeat and never end. And people have memorized, I don't know how many, tens of thousands, if not more, of those digits, and computer scientists have evaluated pi to, billions of digits. Now, people actually tried to prove that pi was either irrational or, if it were rational, what the fraction is for centuries, millennia in fact, and it's actually not that well known who finally sort of knocked the nail on the head and showed that pi is irrational. And it was a Swiss mathematician, in fact. Now, I'm not going to get his name right in terms of pronunciation. In British, we would probably pronounce it as Lambert. I'm sure that's not how his name was pronounced, so probably Lambert, something like that. And he showed this in 1761. So we should celebrate Lambert or Lambert for really a remarkable demonstration that pi is an irrational number, thereby ending millennia of efforts to try and find its value as a fraction. It doesn't have such a value. It is impossible to represent it as a fraction of two integers. It is irrational. Now, we typically don't talk about the diameter when we're sort of doing maths on circles. We typically talk about the radius, and let me draw that as capital R here. Okay, small r or capital R for the radius. And so we have this very, very important result, which is that the circumference of a circle is 2 pi times the radius. And it's good to just get a sense of that. Well, 2 pi, yes, that's a little bit more than 6, about 6.3. So the perimeter of a circle is roughly 6.3 radii around. Okay, precisely it's 2 pi times the radius. Now, we can also talk about the area of the circle. So namely, if I was to cut out this circle, say, and people used to calculate the area of things by cutting them out of paper and weighing them, actually. So I could sort of cut this out and weigh it and determine the area if I knew the weight per unit area of the paper. But that shaded area there, what's the area? A remarkable result. Actually, let's call it A for area. It's pi r squared. Now when I say remarkable, I don't mean the r squared bit being remarkable, because it has to be proportional to r squared. An area of something is a length times a length, and we only have one fundamental length that defines a circle, and it's the length between these two ends of the compass. That's enough to define a circle. So the area has to be proportional to the square of that length. It has to be. What's remarkable is that the number that relates r squared to the area is just our friend pi again. So pi sort of pops its head up again. And what you find in maths is that pi is, it's like a nosy neighbour almost. It's just always around, you know. We'll have a tutorial on volumes soon, and we'll be talking about volumes of, say, the sphere, you know, or cones, and pi makes its way there again. And it's just a number that is so revered by mathematicians because it continually appears in amazing places. However, that's not so important right now, so let me stop waxing lyrical and get back down to business. Anyway, I do think that you want to commit these two results to memory. The perimeter of a circle, which we call the circumference, is 2 pi times the radius, and the area of a circle is pi times the square of the radius. And I think it's very good to have an intuitive understanding that it has to be proportional to r squared. The constant of proportionality is pi. Right, now let's talk about sectors. So let me draw another circle. And a sector is part of a circle formed by essentially cutting out a piece of pie, if you like. We're taking two radii and at some angle from each other, and that defines a sector. Okay, so if I shade that sector there, okay. In fact, I can see I have a different coloured pen within reach, so I'm going to shade this other sector as well somehow. I can't tilt the paper, which is really irritating, but there you go. Right. So we call this the minor sector, and we call this the major sector. And let's just indicate on here the radius. There's the centre of the circle. And essentially the sector will be defined by this angle. So let's call that angle A degrees. Now I don't think you have to memorize the formulas I'm about to write down, but you should understand them. And if you understand them, then you'll be able to reproduce them very easily. So the length of this line, and let me just indicate that in the following way. Okay, so I'm indicating this length here, let's say from A to B around the circle, is called the minor arc. And its length is a fraction of the circumference, and the fraction is A degrees divided by 360 degrees times the circumference. And let's always remember the circumference is 2 pi times the radius. Okay. And the area of that minor sector is the same fraction, A degrees over 360 degrees times the area of a circle. Let's call that just explicitly pi r squared. Okay. So I don't think it's good in maths to try and memorize too many formulas because memory is fallible. These are quite easy to remember from, to be honest, common sense. Just imagine with the area one that you're dividing up some pie with your friends, then you'll very quickly realize that yes, the area of this slice of pie or pizza is just going to be proportional to that angle. So pi r squared is the area of the whole circle, and this sector then will have a fraction of that total area, which is the fraction being a degrees divided by 360 degrees, because 360 degrees is a full circle. So let's just do a quick example. Let's say that degrees, let's say that was 95 degrees, for example. Okay, then that arc AB would be 95 degrees divided by 360 degrees times the radius, and let's say the radius in this circle here, let's say in some units it is 3. Then I have 95 degrees divided by 360 degrees. I then multiply by 2 pi times the radius, which is 3. Okay, and I get, and this sort of problem would be on a paper where you were allowed to use a calculator. So you'd have 95 divided by 360 times 2 times pi times 3 equals 4.97 in whatever units. And then the area of that sector would be the same fraction, 95 degrees divided by 360 degrees, but now multiplied by pi r squared, so pi times 3 squared. So again, bring the calculator to the fore. 95 degrees divided by 360 degrees, multiplied by pi, and then multiplied by 3 squared is 9, and we get 7.46. I'll just put units squared here, okay, because I'm not defining units. Problems are always seems to be set in centimeters, which I just find a bit boring, to be honest, so I'm not going to give any units. They could be light years if you like. It could be talking about a galaxy. Right, very good. So I hope that's fairly clear. If you were asked to find the arc length of the major sector or the area of the major sector, I would recommend probably just to calculate the arc length and the area of the minor sector first, and then you can find the arc length of the major sector by subtracting this minor arc from the circumference, and you can find the area of the major sector by subtracting this area that we found for the minor sector from the area of a circle. That would probably be an easy way to go about it. Alternatively, of course, you could just use these relationships, but to use this angle as your angle. So in this example, it would be 265 degrees would be the angle that you would use. So that's all I have to say, really, I think, about sectors and circumference and area. Pi, people have written books on pi. It's so interesting. Maybe I'll give a tutorial on pi at some point in the future. I just want to say a few words about polygons, and it's actually convenient to draw a polygon inside a circle because it helps understand the things I'm about to say. It also gives me a chance to show you something rather cute, which is that if you draw a circle with a pair of compasses, you can inscribe a perfect polygon by just marking a point on the circle and just drawing radii around. Okay, so we're just going to mark here, and we're going to mark here. And we're going to mark here, and here, and here, and then you see it joins up perfectly. Well, almost, if I had drawn it slightly more carefully. And what we have there are the vertices of a polygon, namely a hexagon, actually. So if you ever want to draw a perfect hexagon, you can do it just with a pair of compasses to mark out the points. And that might seem amazing to you until you realize that a hexagon is made up of 6 equilateral triangles. And so the sort of interior angle of a hexagon is 60 degrees. And there will be 6 of those in 360, which is why with 6 compass sort of manipulations you can draw a perfect hexagon. So here it is. Very nice. Let me just draw a couple of slices here of the hexagon. I'm only going to use this hexagon to illustrate something that is more generic. But it is just pointing out, and to be honest, it's not very deep, but it is worth pointing out. So, let's imagine that I had drawn any old polygon inside this circle, let's say with n sides. If you draw one slice of that polygon, a natural question to ask is, well, what's this angle? And a natural question to ask is, what's this angle here for a polygon? Okay. So let's just do it for the hexagon that we've drawn, but then you'll see how easy it is to generalize. The key thing about the polygon is you need to know how many sides. And to be pedantic, these are regular polygons, meaning that all sides have the same length. So regular polygon with n sides. Here we have 6 sides, so this angle here has to be 360 degrees divided by that number of sides, which in this case then will give us 60 degrees. And then you can see why a hexagon is made of 6 equilateral triangles, because this angle has to be 60, because there are 6 of them in a circle. These are all radii, so this is an isosceles triangle, so these 2 angles will be adding up to 180, take away that angle. So in terms of the hexagon, it's 180 take away 60 is 120, divide by 2, then these are also 60 degrees. Okay, and so that's an equilateral triangle. So this also here is a radius, as we know actually by the way that we made the points on here. This internal angle here of the polygon will be 2 of these angles added together, so will be 120 degrees. So I've illustrated that here for a hexagon, but it generalizes completely. So if I imagined that I had some polygon inscribed in a circle, and I'm going to try and draw this. This is not going to be very good at all, I apologize, but I'm just trying to sketch this really. So this is not meant to be accurate, but let's imagine we drew some polygon inside a circle with n sides. And here are 2 of the slices. The only point I want to make is that this angle here will be 360 divided by n degrees. And these are all radii of the circle, so this angle here will be 180 degrees. Take away this 360 degrees divided by n, all divided by 2. Okay, and so actually this internal angle of the polygon, so this complete angle here, will be just twice this, so literally 180 degrees, take away 360 degrees divided by n. And, you know, when you're sort of deriving things like this, I can't recommend highly enough to do reality checks. And maybe I haven't stressed that enough in these tutorials, but when you get answers to problems, do a reality check. Is it reasonably okay? For example, when we worked out, radius is 3. Well, when we worked out this problem here of this sector, we found that the area was 7.46. Is that a reasonable value? And you can sort of do a little reality check there, because the radius is 3 here, the angle is roughly 90 degrees. So, a triangle would, if I made that into a triangle, it would have an area of 3 squared divided by 2, because I could imagine a square, and that square would have a radius of 9, so half would be 4.5, a square would have 9, so this answer has to lie between 4.5 and 9, and it does, So reality check is just, is my number even plausible? If it fails that test, it's almost certainly wrong, and you need to go back and check. So with this little derivation we did here, to get an understanding of that, let's take a couple of limits here. Well, first, I can just take n equals 6, and I do indeed get back 120, so that's good. I could take n equals 4, I could have a polygon that is actually a square. If n is 4, 360 divided by 4 is 90, 180 degrees minus 90 is 90, and yes, the internal angle of a square is 90. I could take n really, really big. If I take n extremely big, 360 divided by n will go to 0, and this internal angle will go to 180. And that is actually correct, because if we take so many sides that the polygon basically looks like a circle, we're really then just defining this angle to be the angle between sort of 3 arbitrarily close points on a circle, which is really essentially a straight line, and the angle should be 180 degrees. So I'll stop there. I'm just trying to point out that reality checks are quite useful if you derive formulas, especially if you derive them in a hurry, as I did with this one, but that is correct. So beautiful stuff, really. Circles and in 3D kind of related objects like spheres have so many gorgeous properties. And on that note, we will be looking at volumes very, very shortly. And so I look forward actually to seeing you for those tutorials. Until then, I wish you well and see you later.